Okay, so now we begin our third unit of the 5 in this course. And if you look at the section, it's a continuation of kind of the last chapter that we were doing, but we're going to sort of focus this chapter on 4 sections. So it's one of the smaller units of this semester. And it's focusing not on one specific function, but a whole family of functions, if you will. And from this introductory section, we'll get into applications like transformations and composition and one-to-ones and inverses. So we're going to take functions in general and apply different concepts and applications. So we're not going to focus on any one specific one, but so we want to introduce sort of a group of functions that you'll be expected to know. And that's what this first section is in section 3.4, a library of functions. Now, I'm sure many of you have seen all of these before, so I'm not going to go through in great detail and plot points and stuff. But just as a reminder of what they are and some of the domains and range features that will come up. So the first one is your basic one. It's just your horizontal line. It's a function of a constant. And so that constant is just going to be some number, let's say 2, and you would have the function y equals 2. So it's a simple horizontal function. You can think of this as y equals 2 or f of x equals 2 if you want to be more formal with it. But the domain is all real numbers, right? It's any x value can be put into this function, but the range is just that y value. So in this case, it's 2. I'll generalize it and use the letter they use in the notes and say b. So whatever the value is that you're graphing, in our example 2, that's going to be your range, all right? All the y values are the same. Pretty straightforward. Doesn't get much more basic than the constant function. Slightly more advanced, but still very easy, is the identity function, which is just y equals x, right? So think of h of x as y, and y equals x is just your straightforward slope of 1, y-intercept of 0, right? So think of this as simply y equals x. And you've done some kind of symmetry with this stuff before, but just like any linear function, the domain and range are all real numbers. Again, you could plot points if you want to, but I think some of these are pretty straightforward. So then we've spent a lot of time on these functions, the quadratics. Of course, the next step up is the square function, a quadratic function. And your basic parent function is where the vertex is at 0. 1 squared is 1, 2 squared is 4, etc. And you can see the symmetry on both sides. And not surprisingly, it's your typical parabola that opens up. And again, we're just talking about the parent functions, the basic functions. And so we'll do stuff with them in later times, but for now we're just introducing them to you so you know the basic features of them. And just like we've sort of done over and over again, the domain is all real numbers, and at least the range for this specific function is 0 to infinity, right? Your minimum is a 0 and it goes up to infinity, and we've talked about applications of that when it opens down or whatever. So that's your square function. One of the functions we haven't spent as much time on is the cube function, but much like the square, it's just an exponent of 3. And you may have forgotten what this looks like. So you start at the origin, 0, 0, 1 cubed is 1, 2 cubed is 8, so it's sort of off the graph here. And again, negative cube values are still negative. So in this case, it's a steeper version of the square function, but the left side goes down because it's negative, right? And so in this case, while the domain is still all real numbers because anything can go in for x, the range is also all real numbers because you can have negative y values out of it. Okay, so think of taking the square function and kind of flipping it over on the left side, making it a little more narrow, and you have the basic idea of a cube function. All right, sort of like a little river that kind of runs lazily along the y-axis, something like that. Okay, so there's your cube function, and again, we'll apply different things to that a little later. The absolute value function, you've probably seen in previous classes. We don't spend a ton of time with it in this course. We'll do something more with this unit, but after this unit, it's probably not going to be seen much more. But this is your V graph, right? So if you think about the absolute value of a positive number, it's just that positive number back, right? 1, 1, 2, 2, 3, 3. But of course, anything in absolute value, if it's negative, the result is positive. So any negative values inside the absolute value function become positive. And that's where the V shape comes from, right? And so that's your idea there, okay? So again, you can have anything for your domain. You can plug in a negative number or a positive number, but the range of the function is always positive. So much like the square function, the quadratic, 0 is your minimum. Think of it as a vertex, and we'll have different applications of stretching it or compressing it or making it narrower, wider, or whatever, okay? And then the square root function, we've done a lot of square roots, especially with domain in the last unit, so you probably know some of those things, but the shape of the graph, think of the inverse of the square function, right? So if you have the square function where you're taking a value and squaring it, here you're taking the function, taking the square root of it. So the square root of 0 is 0, the square root of 1 is 1, and I'm going to go then all the way to 4. The square root of 4, of course, is 2. Square root of 9 is 3. And so what you get is sort of the flipped version, the reflected version of the parabola. So if you think about this right side of the square function kind of flipped over, you get this version. So it's really just the right side of the square root function. Now notice we don't do the other side because then it fails the vertical line test. So if you tried to do it down here, while that would be a sideways parabola, it no longer is a function, and so we can't do that, all right? And so we're not going to worry about the negative part. We're just going to worry about the part that's a function. So the domain, which you know by now, anything under a square root can't be negative. The domain is the first restriction there, so from 0 to infinity. And likewise, the range can also not be negative. You can't put a number in X and make the square root of it negative. So that is also going to be 0 to infinity. Now, some of you might think, well, the square root of 9 is plus or minus 3. If you're solving a quadratic, yes, it is. But when we're just evaluating numbers, we're only looking at the positive values. So there's never going to be any negative y value on the way out, okay? The cube root function, however, is basically a reflection of the cube function. So take this cube function and kind of reflect it over the y equals x axis, and you have a lazy river, if you will, that looks like this. So 1, 1 here, but instead of 2, 8, flip it to be 8, 2. So you're going to have it go in this general direction. All we're doing is switching the x and the y effectively. -1, -1, and then instead of -2, -8, it's -8, -2. So somewhere over there, the graph continues, and you get your sideways cube function, okay? And that's your cube root. And we could extrapolate this more to 4th roots and 5th roots, but we're not going to get too crazy into them because it's really just a variation on that. And just like the cube function, the domain and range are all real numbers. And of course, we just ended this past unit with rational functions and fractions. And you know, of course, that x can't equal 0 in a rational function, at least the basic function. So whatever the denominator is can't equal 0. So you might know that there's going to be an asymptote there. So we just got to remember that for the domain, you can't have 0. So if we have our asymptote here, there's your x equals 0 asymptote. Right? And if you were to plot points, think of 1 as your x value. 1 over 1 is 1. 1 over 2 is 1/2. 1 over 3 is 1/3. 1 over 4 is 1/4, etc. And of course, you're never going to get to 0, right? Because it's always going to be 1 over something, which gets really, really, really small, but never actually touches the x-axis. Likewise, if you take numbers between 0 and 1, 1 over 1/2 is 2. 1 over 1/3 is 3. So as x gets smaller and smaller, y gets bigger and bigger. But of course, it's not going to actually touch the y-axis because we know there's an asymptote. If you remember your rule about your relationship between the powers of the numerator and the power of the denominator, you'll know that the exponent power for the numerator is 0, and the exponent power for the denominator is 1, which means you're going to have a horizontal asymptote, right? We did that last section. And that horizontal asymptote, when the denominator's power is greater, is going to be y equals 0. And so you're going to have another asymptote across here. So The only thing I didn't do is reflect this. So if you take x as negative numbers, you're going to have the same scenario, but in the negative section. So you can have a graph that looks generally like that. And you can see that the graph is never going to actually touch the x-axis there. And so y equals 0 there. So for your domain, you could either leave it as x not equal to 0, but if you want to put it in interval notation, you can write it like this. Negative infinity to 0, 0 to infinity, and it's the same thing for the range, right? Because there's an asymptote, you're not going to actually touch that value. It's a little more complicated to write it in interval notation. It's a little messy, but you could, if you prefer, write it as y can't equal 0. Of course, MathXL prefers interval notation, but it means the same thing, right? So the key thing to figure out, and you've done this in previous units, is that the domain restriction and the range restriction are 0, okay? And we'll, again, do some adjustments to that. So those are the 8 main functions that we'll care about. And like I said, we'll do more things with transforming them and applying them to other functions later in this unit. But for now, we're just going to focus on those 8 main functions. So in the last rational function, we were just talking about asymptotes and stuff. And so you might remember from last week that when you have a rational function, you have either a whole or an asymptote, depending on whether the denominator factors cancel with the numerator or not, okay? Generally speaking, that is a concept called continuity. And some of you who have taken pre-calculus may have talked about this a little bit in terms of continuity. Now, technically speaking, there are 3 different requirements that have to be met. When we're talking about the definition of continuity, it's more of a calculus-based setting. So we're not going to worry about the 3 requirements of continuity. We're just going to talk about it very generally and very informally. So we'll define it as such. And this is a very fundamental, I guess, basic interpretation of continuity. A function is continuous over a specific interval if you can draw the graph without lifting your pencil. That's sort of a very basic idea, but I think it gets the point across. And here are a few examples of continuity versus non-continuity. In a continuous function, you literally just trace the function, and you never lift your pen, never lift your pencil. There's no breaks in the graph, right? That's the idea. And in basically all of the functions we did up here, they were all continuous. I didn't draw them in one stroke, but I could have, except, of course, for the rational function. So there are different types of discontinuities depending on the situation. If you have a whole, you have sort of this last example here, and so that's sort of what we're familiar with when you have factors in your denominator that cancel with the numerator. So in this particular example, there was a whole that looks like x equals -6 or something like that. And that's fine. It's just a whole there, and the rest of the graph continues on. Now, I don't know what the graph actually is, but because I had to lift my pen to stop and draw the circle for the whole there, that made it discontinuous, right? But it's removable, meaning that if I can define a function that I can essentially fill the hole, I can remove that discontinuity with a second function. And we'll talk about that in the next section here. All right, so that's probably the most common type of discontinuity when you're dealing with wholes. We certainly talked at length about the asymptotes. So here's a graph here, kind of going from right to left, where there's an asymptote based on the function. It's not really drawn very well, but it's basically your rational function that's shifted up and over a few pieces, right? So here's sort of where that intersection of the asymptotes lies. In the parent function, it's at 0. In this example, it looks like it's at 3, 4, right? So whatever reason, you have an asymptote at x equals 3, and then the ratio of the horizontal asymptotes, the leading terms, is 4. Now, unlike a whole, you can't remove it by simply defining a function, right? These are going in completely different directions, and so this is considered a non-removable discontinuity. You can't just define a function somewhere and connect the 2 parts of the graph, right? And so that's what your asymptote is. Sort of a weird one, which leads into the next section, is what we call a jump discontinuity. It's basically 2 functions that sort of interact on the same set of axes. So these are two distinctly different functions that just so happen to be on the same graph. So here's one completely independent function that kind of goes up like that, and then it stops at this specific point on x, and then a new completely different function starts at another point and has a completely different direction to it. So these are two completely defined separate functions that happen to be on the same set of axes. Literally, you can think of it as the graph jumps from one point on an x to another point on the x value. You can't fill it with another function because it's already defined at another point, so that hole never actually gets filled, which is why it's a jump discontinuity versus a removable discontinuity, okay? And so those are your different types. You're not going to have to worry about the names of them per se, but just know that they exist. We've talked about the non-removable ones, the asymptotes, in the last chapter. We did horizontal and vertical asymptotes. You're pretty familiar with those. We even talked a little bit about the holes. This section, we're going to focus on the jump discontinuities, and those are defined more generally as piecewise functions. Now, if you've seen these before, you probably know what they are, but if not, all a piecewise function are basically what we did in that last graph up here, which is two or more pieces of different functions. Right? So we're just taking two different functions or three different functions, however many you want, and then rather than taking the entire function as a whole, we're only going to define it over a specific set of x values, okay? So if you look at that last example in the jump discontinuity, we only defined this linear equation here for specific x values. It only started from 2 and went to x equals infinity, right? If we didn't care about anything less than 2, that was a different function. So let's kind of explore that a little bit more, and we'll see what we mean. All right, so here's sort of an enlarged version of a piecewise function. So here we have two functions. We have a linear function here, and then we have a constant function here, but it's only defined for specific x values. So you want to look at that for your domain, and that's what the first part of the example is. What is the domain of this function? Are there any x restrictions from the given table? And as you can see, every x value is accounted for. If x equals 4, you use the second equation, and if x isn't 4, you use the top equation. That covers everything. So your domain is all real numbers because for every x value, you can figure out which of the two functions you should use. And that's the key of this. Based on what the domain value is, what graph are you drawing? Okay, so what are the intercepts? Well, of course, we know that the y-intercept is when x equals 0. And according to that, x equals 0 means you use this function, right? Because x is not 4, you use that. So spelling this all out, you have negative 1/2 times 0 plus 2, which of course is 2. So your y-intercept is at 0, 2. Now, there may be an x-intercept. We'll look at that in just a second. But from the y-intercept, the key thing is, where does x fit? X is 0. That falls under this restriction, and so you want to plug it into that top equation. And then you completely ignore the bottom equation, right? Because x was 0, x is not equal to 4. It can ignore it, okay? So that's kind of how you evaluate some of the functions depending on the scenario. Sketching the graph. All right, here's where it gets a little bit more complicated. So we'll start with the easy one. When x equals 4, y equals negative 3, right? That's just a point. So when x equals 4, y equals negative 3, there's your point down here. Okay, that's the easy function, all right? The other function, the top function, is simply a linear equation. It's got a negative slope, a y-intercept of 2, and you can draw that. So just like any other linear function, you start at y equals 2, your y-intercept. Your slope is going down 1, right 2, down 1, right 2, down 1, right 2. Now notice what I did as I'm doing this, down 1, right 2. If I plot my line and I draw my graph, I will have an issue because I now have two values of y at x equals 4, which of course fails the vertical line test and therefore isn't a function. Well, these are functions, so we can't have the same x value having two different y's. That's what this restriction is about. It says x can't equal 4, so what we're going to do is we're going to remove that point. That does not exist at x equals 4. That is going to be replaced by a hole, right? So since x can't equal 4 for this function, we have to designate it somehow, and that's what we have sort of as a removable discontinuity, right? So sort of like this function we had up here on the right, where we have a hole in a part of the graph. The rest of the graph continues as normal. So you can still keep going with your plotting of your slope and connecting the points, but you're going to have a stop. So you have this part of the graph, which is there, but you're not going to have a point there at 4. So I'm going to continue my graph going up this way, and hopefully I'll get a kind of a straight line there, and there's my function. So this is that line, right? This is -1/2 x plus 2, but when you get to the restriction at x equals 4, it can't exist. It is defined as some other value at 4. So it's sort of a weird idea, but this is the idea of a discontinuity, and it's a piecewise function, okay? You can sort of think of it as a jump because it's already defined at another point. I guess if that point here at -3 didn't exist, you could call it removable, but since the function does exist there, it's sort of a jump discontinuity. Okay, and so if I were to have drawn this with just my pen, I would have had to have lifted my pen to go over the point 4, 0 and continue on. So there is no x-intercept because it's not defined when y equals 0. Okay, so because of that, the range kind of tells us something. There is no y value at 0. Y never equals 0. It equals everything else, right? It equals -3 twice on the point and on the line, but it will never touch 0. And so the range is just everything except 0. All right? Is it continuous? Obviously not. We were just talking about that, so it's not a problem. But hopefully graphing these isn't too bad. You're just graphing a piece of each of the functions and stopping when the domain tells you to. So let's do another, maybe a little bit more complicated example, and you can hopefully drive this point home. Okay, so here we have 3 functions. We have a simple linear function, x plus 4. We have a second linear function, -x plus 1. And we have a constant function at -5. So it doesn't matter the order you do it in. I like doing the individual points since x is only defined at x equals 2 here with -5. Then you know that the point 2, -5 is on the graph. All right, so if I'm plotting x equals 2, my y value is -5, there you go. And nowhere else will x equal 2. And if you look at the domain restrictions on the first and the third equations, you're not equaling 2 here, you're not equaling 2 there. So the function requirement is met because there's no issue with the x. And now we just graph the other 2 pieces. X plus 4, but we only graph it from -6 to 2. So when x is -6, what's the y value? And you can plug in a few points if you want to kind of do a chart. We don't care about anything less than -6 because this is where our domain starts. So our domain starts at -6, there's nothing less than it, and it goes to 2, it goes past 2, and even goes greater than 2. It'll go all the way to infinity, right? There's no upper bound, and so your domain is going to be from -6 to infinity. And that's how you read these columns here. It'll always go in order from left to right. So whatever the top equation is, the very first x value is where your domain begins, and whatever your bottom function domain is where it ends. Excuse me. Okay, so that's your domain, and now we just want to draw that. So from your intercepts, of course, when x equals 0, we're going to use this function. X equals 0 is the top function, and 0 plus 4, of course, is 4. There's going to be an x-intercept. We don't know where that is yet, but we'll see that when we graph it. All right, so let's graph it. X plus 4. Well, your y-intercept is 4. And your slope is 1. Now, according to the domain, we don't equal 2, it's less than 2, because we've already defined 2 on the bottom of the graph, we can draw a hole there at 2. So it's not going to exist at 2. So that's how we acknowledge that we get really close to 2, but don't actually touch it. Continuing with the pattern, we go down to -6, which is going to be -2. This is included because it's not equal to, or it is equal to, and so you connect them there. All right. Okay, so then we have the third function, which is -x plus 1. Same idea. Now it's a little trickier here because we're not starting at the y-intercept, because according to this, x is greater than 2. So if you think about it, you could start at the intercept of 1 and have your slope go down, -1, but we don't want any of these points because our graph starts at 2. So technically, if we were to continue drawing these points, we'd have our general sketch of the graph, but we have to stop because we're not going to use any of the values that are to the left of 2. So these points get deleted. Okay, so those points get deleted. And instead of having a hole or a point at -2 there, we replace it with a circle. All right, so that tells us that x doesn't equal 2 for this function, and now we can connect our line. Okay, so it's just like the line -x plus 1, but it starts at x equals 2 at that point, well, x greater than 2. So hopefully that makes sense. Think of it as 3 complete functions, but you're only defining them for certain types, right? And so I guess we didn't need these numbers up there. We can delete that. We're not going to give you any really super complicated functions. I think maybe we'll get to like an absolute value type function when it comes to this, but we're going to restrict it. And so the key thing is just make sure you're focusing on this domain section, right? This is really the key element of it because those are the parts of the graph that we want. And so hopefully as you practice this more on MathXL and ask questions in class, this will make a little bit more sense. Okay, now one thing we didn't cover is the other intercept, and you'll notice based on when we drew our graph that there is an x-intercept there. Now there wasn't necessarily an algebraic way to solve it, so that's when you graph the function, you'll be able to see it there. Okay, so that's kind of the way to get the x-intercept. The range, now you want to look at the graph. So this graph goes all the way down to -infinity, right? This graph kind of suggests it's going down. I guess I can highlight that rather than draw another line. But this graph is going all the way down. So that means, of course, that our range starts at -infinity, right? And so as you crawl up the graph, we're covering all the y values. And even at this point where it's not defined here, it is covered here. So we can keep going. Now we sort of jump over to this graph, and then we can go all the way up, all the way up, all the way up, and we stop right at 6. The y value here is 6. It's not quite touching it, so we are going to stop at 6 with a parentheses, right? So think of this as all of the y values are in the graph that are less than 6, right? There's nothing above 6 or even equal to 6 in this graph. And so the range is a little bit trickier to find. You have to graph it first and kind of look at it. There's no real algebraic way to approach it. But that's how you look at the range. So once you understand graphing the functions, I think everything else comes from that. So just make sure that you're understanding how to graph these functions, because if you don't know how to do that, then everything else is going to sort of fall from that. So again, if it's a little bit tricky for you, if it's going too fast, please ask in class, but hopefully many of you have at least seen it in Algebra 2. Is this continuous on the domain? Of course not. We have 3 separate graphs. It's absolutely not continuous. Okay? So that's piecewise functions in general. There's one specific type of piecewise function that gets its own sort of function with it, and I'll talk about this on the calculator in a second, and that's called a greatest integer function, right? Or maybe you think of it as a step function. Some of you have heard of it in another term there. But the idea behind a step function or a greatest integer function is that it's defined as the greatest integer less than or equal to x. Okay, so I'll explain what that means in the next example, but when you're done with the graph, the entire function should look like, hence the name, a bunch of steps. So think of it as horizontal lines leading up or down, okay? How it's written, it's sort of weird. It's got this kind of double bracket feature, so if you see it written that way, on your calculator, it's written as int x, and I'll show you where that is on the calculator in just a second. But they mean the same thing, but that's what the greatest integer function looks like. The nice thing about the greatest integer function is every x value is applied, right? All of the x values are taken into account. So here's how it works. If you think about graphing the function, let's take just some practical x values. So we have, let me move this down here because we'll answer part C a little bit later. So we'll have our x values and we'll have our y values. If you start with an integer, the answer is pretty easy, right? So if I start with x equals 1, what is the greatest integer less than or equal to 1? Well, 1 is the greatest integer less than or equal to 1. What's the greatest integer less than or equal to 2? 2. So at each point, 1, 1, 2, 2, 3, 3, 4, 4, 0, 0, we can go negative, we're fine, right? So greatest integer less than or equal to -1 is -1, -2, -2, etc., right? So those are pretty straightforward. It looks a lot like you can just connect the points and have a slope of 1. It gets a little tricky when you have non-integer values. So keeping this chart going, let's pick a number, say 1.2. What is the greatest integer less than or equal to 1.2? Well, 1 is the greatest integer less than that value. 1.3, it's 1. 1.4, it's 1. 1.99999 is 1. So for every value from 1 to just about 2, I'm going to zoom in just so you can see it, from 1 just to about 2, it's the same y value over and over. It's always 1 until you get to the next integer, and then you repeat it. So when you get to 2, 2.1 is 2, 2.2 is 2, etc., etc. And so that graph is going to be a horizontal line up until it gets to 3, up until it gets to 4, etc., etc. And so as you create this graph, it just keeps jumping to the next y value. And you can see this sort of collection of steps. It gets a little tricky with negative values, but if you understand the table, you're in good shape. But if you think about negative values, let's just take some examples, right? If you don't have the graph, it's a little bit trickier. The graph, of course, gives it away, but let's say you have a value of -0.5. Well, what's the greatest value, or the greatest integer less than -0.5? Well, that's -1, right? The greatest integer less than -1.3 would be -2. And so if you plot those points, when x is -0.5, the y value is -1. So it's consistent with what we've been drawing. But a lot of people just take a look at the positive values and go, oh, it's 1.2, I go to 1. It's 1.3, I go to 1. 2.1, I go to 2. -1.3, I go to -1. But the negatives are tricky. So you got to make sure that you're going to go to the next lower integer. All right? And so that's what the graph is, and you can see the steps just keep going and going. It's fine, no problem. And that's the idea. So that's a step function. You can find it on your calculator if you go to your math button, and I'll do this on the online calculator too here, but the math button, and then go to num for number, and then option 5. And it's written as int parentheses, okay? So I'll show you on this calculator here and how it looks. So if we go to y equals, if you find your math button, go to num, and then you can see that 5th option, right? 5th option is integer, put your x in there, and there you go. If your window is such that it's -10 to 10, your basic standard window, you can zoom 6 your calculator and graph it, you can see the step function. Now, an interesting thing about this graph, you see the green lines that show the graph. It looks at that the origin, the calculator, the app, makes a mistake because the step sort of breaks its pattern here. So if I zoom in, I'm able to touch the graph, and I can't touch anywhere on the graph that's not a function. Like you see in the green, it says x equals 2.28, y is 2. And you can do that for each of the steps. Now, as I move the graph to the left, the picture sort of does it a disservice. Here I can see 0, but notice I can't move my graph to where that negative green line is. If you look at the point, -6, oops, let's try another one. Let's try negative 1.45. You see it's lined up at -2. If I go to, zoom in here, if I touch the graph, notice where the little coordinate is, -0.51, y is -1. This part where you see the purple kind of crosshairs should be a green line. The app is wrong. This green line up here at the x-axis is not supposed to be there. When you graph it on your calculator, you'll see a correct graph, but I thought that was an interesting little error. The points are correct, and the purple line is where, or the purple intersection is where the green line should be. It just isn't. It's on everywhere else except there. So it's sort of an interesting mistake that the app makes, but whatever. It is what it is, and your calculator, of course, will get it right. So that's your greatest integer function. We'll end this section just by kind of applying this a little bit. We have two examples that sort of work backwards or apply it in sort of a word, real life scenario. In this case, these examples are giving you the functions, and you've got to write the actual function itself. Right, so here's your functions, and you can kind of see, I'll highlight them in blue in case it's harder to read. You have a graph here with an open circle there. You have a horizontal line here, and then you have another open circle there with a line going down, okay? So there's three different functions. So if we write these functions, we can think of this as f of x. And what I write, I kind of like write a little brace here. If you can't write them, it's no big deal. But I want to leave enough space to essentially draw or write three functions, okay? So that's what we're going to write here. And I'm going to go left to right because that's just how we think. And so what is this function? Well, you can figure out that this is a linear equation because it's pretty straightforward. And of course, it needs a slope and a y-intercept. So if you look at the line, the slope, if you look at points on here, the slope would be -1/2, right? So your slope here is -1/2 x. And if you completed the pattern, it would cross the y-axis there. So it's about -1.5. I'll call that -3/2. But I have to define it. It only exists when x is less than -1. So that's the restriction you want to write. If x is less than -1, this graph exists, right? And there it is. When x is less than -1, there's your graph. The horizontal function, pretty straightforward. The y value there is 2. So 2 is your second function, and it only goes from this point to this point. That's x is -1 to x is 3. All right, we're including those points. So -1 to 3, right? And you're including them, so don't forget your equal signs, okay? And then your third function is another line. In this case, the slope is negative again, and it looks like the slope is -1. So -1x, all right? So -x. Now here it gets a little bit more conceptual. You've got to figure out if the pattern continued, where would it cross the y-axis? What would the y-intercept be? And if you use your pattern, you can count the y values, and it would give you 7. So -x plus 7 is going to be that feature, but only when x is greater than 3, right? So there's an open circle at 3, and the graph goes down. And you can see, based on how you've written it, every x value is accounted for, right? It doesn't equal -1 in the first graph, but it does in the second. It doesn't equal 3 in the third graph, but it does in the second. So all of your x values are accounted for. It's a function by definition. It doesn't fail the vertical line test, and you've got your piecewise function. All right? So if you understand maybe writing the equations, it might help you going backwards when you're graphing them. All right? And just continuing on with this idea, we're going to have two functions here. We'll call this, apparently it's g of x. Not that that really makes a difference, but g of x. We have two functions. The first function, again, is a linear function with a negative slope, and this one's pretty straightforward. The slope is -1, and your y-intercept is 2, right? Or -2. It just is right there, and that's only for when x is negative, so less than or equal to 0. So from there, moving to the left, there's your function. And then it jumps, and now you have a function here that has the same slope, positive here, and +1 is your slope, right? It goes up by 1s, so positive x. If the intercept existed, it would be at 2, so you can still write that as a function, but we separate that and say, well, we're not going to count 0 here. We're just going to say x is greater than 0. If it was equal to, it would have certainly been a y-intercept of 2, but the y-intercept is actually -2, right? If you're asked what the y-intercept was, that's what it would be. All right, and so that's the basic idea. You have a function that goes to the left and a function that goes to the right. Okay, and then finally, if you want to do this one on your own first, maybe pause the video and see if you can get it. I will highlight the fact that this is hard to see. There's a point there, and then you have the lines here. So if you want to try to see if you can create the function yourself before you see the answer, that's totally fine. But when you're back, here's what it would look like. So you have h of x, and again, we have 3 functions. Hopefully I have enough room to write here. This equation has a negative slope. It's got a y-intercept of 0, so you don't have to worry about a y-intercept, and it's only for when x is less than 3, right? So if x is less than 3, all right, there's 2, there's 1. At 3, if x equals 3, then we have the point here, which is simply the point 1, and then we have a constant function here, y is 3 if x is greater than 3. Okay, so they're not too crazy. Linear functions, constant functions, we have a point. It's pretty straightforward. You know, we might throw in a parabola here or there, or an absolute value here or there, just to kind of jazz it up a bit. But that's the idea of piecewise functions. Okay, and then we will end with a word problem, but we give you the functions, which I think makes it a lot easier. It's a scenario where we have a gym membership, and there's some restrictions to it. So there's a month membership plan where it's $40. So regardless of how many classes, how many fitness classes you take, it's going to be $40, and that's sort of what that suggests. And you get 2 free, right? So when x is less than or equal to 2, you still pay $40. If you take any additional classes, it's $15 each. And so that's where this 15 comes in once x is greater than 2. And the only real thing you have to worry about in this example is which function to use. And that's where you have to pay attention to these domains, right? So when x is 1, obviously x is 1, that's between 0 and 2, your cost is $40, right? You probably didn't need to do math for that. It just was common sense. Since you had 2 free classes, if you only take 1 class, it costs you $40. If you take 3 classes, you can think of it as one of 2 ways, 40 plus the additional 15, or if you wanted to get, mathematical, you could plug in the 3 into the bottom function. And that's the thing I want to point out, is that when x is 3, you're going to use the second function. And obviously 15 times 1 is 15, plus 40 gives you 55, right? So common sense and logic told you it was 55 as well. But when you get to bigger numbers, it might be a little trickier. Whether or not you take any class, you could take 0 classes, it's still going to cost you $40. And if you take 6 classes, you can just think of 4 groups of 15, right? You have 4 classes that you're paying for. 6 minus 2 plus 40. So you can think of it as 4 classes that you're paying for at $15, and that gives you an even $100. Okay, so I think that's pretty straightforward. The trick there, and this happens in previous years, so I bring it up now, is make sure you're plugging x into the right equation. If you plug it into the wrong equation, all bets are off, and you're going to get the wrong answer. So just pay attention, but you should be okay. And if you made it through this video, thank you for listening. You should be good to do the next Math Excel assignment.